Okay, here we go. Good morning, everyone. Hi. Great, great. So we're talking currently about randomized algorithms and the analysis of randomized algorithm. And I'd like to use the opportunity to recap primality testing, testing whether a given natural number is a prime number or not. And what I'd like to emphasize is that the naive approach will not give rise to a good algorithm. What is the naive approach? The naive approach is guess a proper factor. So you're given input, some natural number, and in order to check whether this number is prime or not, a naive randomized algorithm might try to guess a factor, a proper divisor of that number. And if such a divisor is found, then indeed the number is not prime, right? And if no such divisor is found, then maybe we want to apply this amplification technique that we talked about. But the point is, this naive approach does not give any reasonable algorithm because we have no good bound on the error. What is the error of this naive approach? The error is when the algorithm fails to detect, fails to guess a proper factor, although there is a proper factor, right? So one-sided error, whenever the algorithm finds a proper factor, then it will correctly reply that the given natural number is composite, is not a prime number. But when the number is actually composite, our randomized naive algorithm might fail to find such a proper factor. And I'd like to estimate the probability of this kind of one-sided error, and it turns out that this probability is very large. Namely, to this end, let's first play a little game. I think of a number between 1 and 10,000. Natural number between 1 and 10,000. And I'd like to ask you to guess that number. So if you are supposed to guess the number that I'm thinking of, what is the probability that you guess the right number? What is the probability that you guess the number I'm thinking of, a number between 1 and 10,000? So this is a question for all of you. What is the probability that you guess the right number between 1 and 10,000 that I'm thinking of? Yes, indeed, 1 over 10,000. So let's now apply this to so that's a very low probability, right? Or more generally, if the number I'm thinking of is between 1, or let's just make it 2, between 2 and square root of x, what is the probability that you guess the correct number between 2 and square root of x? Well, it's roughly 1 over square root of x, right? 1, whether it starts from 1 or 2 asymptotic doesn't make a difference. But when I just give you the promises that my number is between 2 and square root of x, then the probability that you guess that number is roughly 1 over square root of x. And this is actually exactly the case, the worst case of our randomized algorithm. If the input is composite, if the input is the product of two primes that maybe have roughly the same size, maybe it's a square number, the input, then it's certainly composite. But in order to detect that it is composite, the algorithm has to guess that prime factor, right? And when the input number is x, then that prime factor will be somewhere between 2 and square root of x. And the probability for this algorithm to guess that one single number, that's exactly 1 over square root of x. That should be 1 over square root of x. So that's a very small probability. And that's so small a probability that we cannot even amplify it. Okay. So that's why this naive approach doesn't work. And instead, we've seen a more sophisticated approach, the Miller-Rabin test, that makes heavy use of number theory. We didn't prove correctness, but the correctness and error estimate follow from the following purely number theoretic theorem, namely test that equation star, and if that equation star holds, then x is composite. That's the same as for our naive algorithm, right? If it finds a proper factor, then the number is composite. But the difference is that conversely, when the number is composite, the probability for detecting it to be composite is here much larger. It's a constant, it's at least 1 over 4. Whereas in the naive algorithm, the probability is 1 over square root of x, which is not a constant, it depends on x, right? Actually, it's exponential in the length of x, right? So remember, n usually is used to denote the binary length, and the binary length of x is roughly log x. So square root is 1 over square root is exponentially small in the binary length. So that's very small probability. And therefore, the naive algorithm is not suitable for randomized tests, whereas the Miller-Rabin algorithm is. Now, you might say it's very rare for an input number to be the product of 2 primes, and that's true, but that's not the question we're asking when we analyze randomized algorithms. When we analyze randomized algorithms, we want to estimate the error probability for any possible input, not for average input. That's average case complexity, right? So this idea here, that's kind of a mix of an average case and probabilistic analysis. This is not something we will pursue further in this course. The first analysis is a standard analysis for randomized algorithm, where the input is arbitrarily, and in particular it could be a worst case input, and we only analyze the error probability subject to the internal guesses and conflicts made by the algorithm. That's one thing I would wanted to repeat. And the next thing we talked about is this randomized identity test, Blackbox polynomial test, where the given polynomial is identically 0. And we've seen an analysis of a very simple algorithm, a generic algorithm, namely the following analysis. Due to Schwartz and Zippel, Miller and Lipton. So here we suppose we have a polynomial in n variables. That is not the 0 polynomial, but we have a guarantee, promise that its degree is at most d. And the Blackbox algorithm proceeds as follows. It fixes some finite subset S, and it samples numbers from that set, one number for each variable, and then it plugs in these numbers into the variables. It queries the value of the polynomial on this tuple of arguments. And of course, if the result is non-zero, then the algorithm knows and will correctly report that it's not the 0 polynomial. However, what we're interested in is to analyze the probability of this other case, false positives, if you like, namely when the algorithm reports that the polynomial is the zero polynomial, but the numbers it has plugged in happen to lie on a root of the polynomial, so that the algorithm seems and reports, the algorithm thinks and reports that this is the zero polynomial because the value it has happens to be a zero. This is a one-sided error, and we want to analyze the probability for this error. And intuitively, this should be a small probability because the set of roots, the set of zeros of a multivariate polynomial is a set of measure zero, right? Remember this example of the unit circle for the quadratic polynomial x squared plus y squared minus 1. Here the zeros are infinitely many zeros, all points on the unit circle, but this is a set of measure zero compared to all possible pairs x and y, that is to, for instance, the measure of the unit square, right? So the unit square has measure 1, but the unit circle in this unit square has measure 0, so there should be a very small probability for accidentally hitting this unit circle. And more general, if we have a polynomial of degree d in n variables rather than 2, then still the probability should be small. And we have analyzed that probability, so let's kind of recall this analysis. And the analysis subdivides the sampling and evaluation process in two stages in order to perform a proof by induction. Namely, so the algorithm samples n values, and we subdivide that. First, the algorithm samples n-1 values for the first n-1 variables, and then in the next step, the algorithm samples the final value for the nth variable. This is just for the purpose of analysis, and since the samples are supposed to be independently, that doesn't make any difference if we suppose that the sampling proceeds in these two stages. And the benefit of that analysis is that now we can kind of proceed by induction. After having sampled the first n-1 variables, then we can kind of apply the induction hypothesis. The induction hypothesis is that this claim is true, this bound on the error probability is true for n-1 varied polynomials. So that's a proof by induction. And the nice thing is that the right-hand side indeed does not depend on n. The right-hand side depends on d, the bound on the degree, and on the cardinality S of the set from which the individual variables are sampled from. And remember that there are two ways of making this error probability small. One way is by making the set S very large, but there's a more efficient way, namely if we make the set S just, let's say, twice the size of D, then this error bound will be 1/2, and then apply error probability amplification. This is much more efficient than making the set larger. So for instance, in order to make this error probability less than 2 to the minus 100, our standard reliability bar, then we would need the sample set to have size 2 to the 100 times d, which is a huge set, 2 to the 100, right? So it's much more efficient instead just to have S twice the size of d, and then repeat the algorithm 100 times. Just 100 times, then rather than 2 to the 100, you see how this is much more efficient. And in our analysis, we've used the following general estimate for conditional probabilities. I'm not going to repeat the argument for that estimate, but I'm going to repeat that we will apply this to the case where A denotes the event we're interested in, namely the probability that that the sample hits a root. That's kind of the one-sided error probability. And B will denote the probability for the induction hypothesis, namely that the first, when we have a polynomial in n-1 variables, and we plug in the n-1 values, then the probability for that is bounded according to this expression. So, and another ingredient in this proof by induction is that we write a polynomial in n variables as a polynomial in one variable, the last variable nxn, but whose coefficients are in turns polynomials in the first n-1 variables. So that's one way of looking at multivariate polynomials. Another way is looking at by considering just a linear combination, a sum with complex coefficients of monomials, of products of the variables. But here it turns out beneficial to have this other perspective. Namely, we write this polynomial in n variables as one polynomial in one variable, xn, raised to various powers, with coefficients that are now not just real or complex numbers. That would be our standard univariate polynomial, but with coefficients that are in turn polynomials, namely polynomials in the remaining n-1 variables. And an important observation is, since we're talking about the total degree being bounded by D, so what is the total degree of, for instance, this product? Well, it's the degree of this single monomial, which is J here, plus the degree of the remaining polynomial, right? That's a benefit of talking about the total degree rather than the maximum degree. The maximum degree would say that the degree of this whole product is the maximum of J and the degree of this. But here it's the sum. And since we are promised that the total degree is at most D, that means that the degree left for this part, for the n-1 variable polynomial, will be at most D minus J, because degree J has already been spent here. So this will be helpful in our induction step. So this is a n-1 variate polynomial. That's why the induction hypothesis applies. And it has degree at most D minus J. Okay, so let's now do the analysis with the induction step. And to this end, we're going to look at the, in a sense, the degree of this univariate polynomial. What's the degree of this univariate polynomial? It's the largest value J, such that this coefficient is non-zero. This polynomial is non-zero. Okay, so for instance, when J is equal to 0, then this polynomial may or may not be 0. If it's 0, then this term is entirely absent. If J is 1, this polynomial may be 0 or not, and so on. And we keep looking in our analysis, not algorithmically, for the largest J, such that this polynomial is non-zero, because then we can apply induction hypothesis. The induction hypothesis applies only to non-zero polynomials in n-1 variables. And namely, it says that the probability for such a polynomial, when evaluated according to this process to be 0, that this probability is at most D minus 1 divided by S. So this probability is at most this expression by induction hypothesis, because Pj is a non-zero polynomial in n-1 variables, and we have created the values for these n-1 variables exactly in that way that we've described the algorithm, namely sample the values from the n-1 variables independently at random. and only after that we sample the value for the for the nth variable. So indeed, this is exactly what the Schwartz-Zippel lemma is about in induction hypothesis. Okay, so we have this bound, and now let's look at this term. So this is according to this probability estimate. The probability for the event A, this is our A here, is at most the probability for the event B, this is our event B, plus the probability for A, this is our A, conditional to the probability of not B. This is exactly the event not B. So this is indeed, this inequality is precisely a consequence of this general estimate on probabilities. Now it remains to estimate this probability. Right? But again, this is easy because this is not just a univariate polynomial, right? So we have sampled the values for the variables x1 to xn minus 1. And since this is a conditional probability, we are guaranteed, we're promised that when plugging these values into the jth polynomial coefficient, it gives rise to a non-zero number. That's important to keep in mind, that is the difference between a polynomial and the value of a polynomial. And before we sample and plug in, it's a polynomial. But here we have sampled and plugged in values and are guaranteed by the conditional probability that the value is non-zero value. So this is a non-zero expression. It's a number, a coefficient to this univariate polynomial, right? So we've sampled all these variables so that all the pj polynomial coefficients have become numbers. Then before we sample the nth variable, this is just a univariate polynomial. And we're interested in, before now we sample the nth variable, what is the probability for this nth variable to hit the root of this univariate polynomial? Let me emphasize that again. Once we have sampled the first n-1 variables, all these polynomial coefficients have become ordinary numbers, and the whole polynomial here is just a univariate polynomial, and we know its degree. What is the degree of this univariate polynomial? It's j, right? And because we promise that the jth, the largest coefficient which is non-zero, is indeed still non-zero even after plugging in the values. That's the conditional probability here. And now we sample the nth value. And what is the probability for this now to hit a root after of this univariate polynomial of degree j? Well, again, we can apply the induction hypothesis. That's j divided by s, right? So the degree of this univariate polynomial is j because that's how we chose j, right? We chose j to be the largest number such that this polynomial coefficient is non-zero, which means that for all larger j's, this coefficient is identically zero. So this whole expression is, as a univariate polynomial, has degree j, and it's actually equal to degree j because of this condition. It says that the j coefficient is non-zero. So again, by induction hypothesis, this probability is bounded by degree, which is j, divided by the size of the sample set S. And now it's just mathematics to combine these two expressions, adding them. The denominator is the same already. D minus j plus j, that's just d. So that concludes our induction step. Let me also remind you of the induction start. The induction start, n equals 1. That's just a univariate case. This is a case that is covered by the main theorem of algebra. Any univariate polynomial of degree at most d has at most d roots. So the probability of hitting one of these d roots is just by ordinary probability, the number of good outcomes. divided by the total number of outcomes. The good outcomes are those where we hit a root, one of the D, divided by the total number of outcomes. That's when we hit any value in S. So, and this concludes our recap of the proof of the Schwartz-Zippel lemma. And we've also already seen how to apply this. Namely, we choose S to have roughly twice the size of the degree bound. And then we repeat this using probability amplification. And I say this because you will have next programming assignment will involve implementing and trying the Schwartz-Zippel polynomial black box test for identity testing. Okay, so what are we going to apply this to? Advice, the application is testing whether a graph has a perfect matching. So remember what it means to have a perfect matching. You may remember this from discrete mathematics. A perfect matching is a subset of the edges so that every vertex is adjacent to precisely one of the edges in the subset. Not zero edges, that means the vertex is kind of unmarried, right? Remember what is the literal meaning of a matching? Matching is making a couple get married. That's a matchmaker. So every vertex being incident to one edge means everybody gets married. And every vertex being incident to at most one edge means monogamy. Everybody gets married to at most one person, at least and at most. But here we want to take a different perspective on what it means to have a perfect matching. And then we want to look at it as a mapping from vertices to vertices. So here we define a perfect matching of a graph is a permutation of its vertices. That is a mapping from vertices to vertices such that when for every I, the pair I and mu of I, that should be pi of I should be an edge. So imagine this mapping to assign to every person in the graph its spouse, male or female. Then, of course, the couple that is married from person I to its spouse, that must be an edge. That's the first condition. And the second condition is that all cycles of this permutation, remember the cycle decomposition of permutations from these discrete mathematics, all cycles are supposed to have length 2. Let's look at some examples from this perspective. You can see that these are matchings, and only the second example by item B has a perfect matching where everybody gets married, right? Whereas in example A, these two nodes remain unmarried, and we cannot marry them if there's no edge between these two. And if we try to marry this vertex to someone else, that someone else is already married, so that's not possible. And the same for this vertex. This is a triple count example, because this has an odd number of vertices, and of course a perfect matching only exists in a graph with an even number of vertices. But let's now look again at the perfect matching here in example B from the perspective of these cycles, right? So what is the permutation we're interested here in this case? The permutation maps this vertex to this vertex and maps this vertex to this vertex. So this is a cycle of length 2, right? This gets mapped to here and this gets mapped here back. So when we apply this twice, then we're back in the original. That's the definition of a cycle in a permutation. But there's only 2 vertices covered. For the remaining vertices, this gets mapped here, and this gets mapped here, this gets mapped here, and this gets mapped here. So that indeed, we can consider the perfect matching in this graph also as a permutation on the 6 vertices decomposed into 3 cycles of length 2 this cycle, this cycle, this cycle. And this is the perspective we want to adopt for the rest of this chapter. And you can easily see that this is the same as the notion of perfect matching that you are familiar with already. Right, and actually Jack Edmonds has found a polynomial time algorithm for checking whether a graph has a perfect matching. Edmonds in 1965, it's the so-called Blossom algorithm. Now, if you have maybe or will take a algorithm on advanced graph theory, for instance, by Professor Stangl Om, then you will learn what it is, what this algorithm is, and all the combinatorial graph structures involved in this algorithm. It's called Blossom algorithm because it indeed involves petals and flowers. But this is not the purpose of this course. In this course, we will look at a much simpler algorithm, but a randomized algorithm, not a deterministic one. And this is an algorithm that you will also be asked to implement in ALICE at some stage. Maybe an algorithm, sorry, an algorithm based on this black box polynomial test that we've learned about in the previous slide. So this is a very nice application. And to this end, we rephrase the question whether the graph has a perfect matching as the question whether some multivariate polynomial is identically zero or not. And this transformation from graphs to multivariate polynomials is based on the Tutte matrix. So the Tutte matrix is a matrix which has size n, where n is the number of vertices, so an n times n matrix. And the entries of this matrix are sometimes they're in the number 0, and sometimes they're variables. So this is maybe also called a symbolic matrix. So the entries are mixed variables and numbers, 0. Namely, the variables are xi or minus xi, and the numbers are 0. So the entry is xi plus xi if there's an edge from vertex I to vertex j, and if I is less than j. So the plus sign indicates that the variable corresponds to an edge where in increasing order of vertices. So we take an arbitrary ordering of the vertices. Here we just use natural numbers to indicate vertices, and when the second number is larger than the first, and this is an edge, then we assign the variable plus xij. Whereas otherwise, if the edge goes from a larger vertex to a smaller vertex, then we still use the variables with smaller index first, but we use the sign -1. So observe that in this case, when I is greater than j, then the first index of the variable is less than the index of the second variable. So we only use variables where the first index is smaller than the second. And if we look at an edge that goes from a larger vertex to smaller, then we flip and add a sign minus to reflect that. Okay, so now you know what the Tutte matrix is of a graph. We start with the graph, and then we form this Tutte matrix involving number 0 and involving positive or negated variables. So symbolic matrix. And now we look at the determinant of the symbolic matrix. So remember Leibniz formula for the determinant. Determinant is the sum of all permutations of the vertices, the sign of the permutation, times this product with the matrix entries. Okay? Right, you know that. And remember also what is the sign of a permutation? The sign of the permutation, or one of the many ways of looking at the sign of the permutation, is to say that this is the parity of the number of odd cycles in the cycle decomposition. So this is maybe something to recap in your course on basic linear algebra. So you take a permutation and you decompose it into cycles. And then you count how many odd cycles are there. So cycles of length 1, 3, 5, 7, and so on. These are cycles of odd length. And you count how many of them are there. And if there's an even number of odd cycles, then the sign of the permutation is positive. And if there's an odd number of odd cycles, then the sign of the permutation is negative. This is one way of defining the sign of a permutation. If you have learned a different way, don't worry, both are equivalent. And you're encouraged to look up the proof of equivalence from your basic linear algebra class. Okay, so looking at the Leibniz formula of the determinant, it's easy to calculate the determinant, but it's very costly because this sum here, this sum opens over all permutation. And how many permutations are there of n objects? There are n factorial many permutations, and that's exponential, right? So that means naively evaluating this sum incurs exponential cost, and we're looking in an efficient algorithm that is supposed to be polynomial time algorithm, right? On the other hand, we fortunately have a means of calculating the determinant in polynomial time, namely first bring the matrix into echelon form, and then just take the product of the diagonal entries. This is basically calculating the determinant using Gaussian elimination. Again, you know that Gauss algorithm from linear algebra, and this is a way of calculating the determinant in polynomial time, actually in cubic time, right? The Gauss algorithm has cubic time, but there's a problem with that, namely Gauss algorithm requires and involves a pivot test, testing whether entry in the matrix is 0 or not. And we cannot perform such pivot tests with symbolic matrices because, well, we can, but the next step after having found a pivot, then we divide by the pivot, right? We try to normalize the entry of the matrix, and this is not something we can do here. When the matrix entry is a variable, we cannot divide by a variable. Then we leave the realm of polynomials, and we talking about rational functions, which is an entire mess. Actually, large parts of algebra nowadays are interested in varieties and polynomials and sets of roots of polynomials. So baseline is we cannot apply Gaussian algorithm, Gaussian elimination to symbolic matrices. We can only apply them to matrices whose entries are numbers. There we can divide, there we can test whether number is 0 or not, but not for a variable. So to summarize for now, so the determinant of the Tutte matrix, the Tutte matrix is a matrix whose entries are both numbers and variables, and therefore the determinant of the Tutte matrix is not a number, but it's a polynomial. It involves the variables of the Tutte matrix, and there are at most up to n squared such variables, actually n times n minus 1 variables, right? Of course, the second index is always larger than the first. So it's a n squared varied multivariable integer polynomial, right? So the coefficients are plus or minus or 0, integer polynomial, and its total degree is at most n. This is something you can read off from the Leibniz formula, namely each single term here, each single monomial has at most n terms, and therefore the total degree is at most n. The maximum degree is actually 1, right? Every variable occurs with only power 0 or 1, but the total degree is actually up to n. Okay. And we want to test, this is our goal, whether this multivariate integer polynomial is the zero polynomial, because we're going to prove the following theorem: the determinant of the Tutte matrix is 0, identically 0 as a multivariate polynomial, if and only if the graph has no perfect matching. So this is the already announced reduction from testing whether the graph has a perfect matching, can be rephrased as testing whether a certain multivariate polynomial is identically 0 or not, and namely the polynomial is the determinant of the Tutte matrix. By the way, this is not the Tutte polynomial. There's also a polynomial called Tutte polynomial. This is also related to graphs. A very interesting polynomial, lots of study, but this is not the polynomial we're talking about here. Here we're talking about the determinant of the Tutte matrix, which is a multivariate polynomial, but this is not called Tutte polynomial. So how do we test whether this polynomial is identically 0? Well, one way of testing whether such a multivariate polynomial is 0 is by looking at all its coefficients. But as I said, there are exponentially many possible coefficients according to Leibniz formula, right? For every permutation pi, there's a possible coefficient, and we cannot afford to look at all of them, exponentially many of these coefficients in polynomial time. On the other hand, we cannot even calculate also this determinant because it's a symbolic matrix, and we cannot apply Gaussian elimination to matrices whose entries are variables. We cannot test, for instance, whether the variable is 0 or not. The pivot test, that depends on what is the value of the variable, right? On the other hand, evaluation, that's easy. Evaluation means fixing some values for the variables. And once we have assigned values to the variables, then the variables become numbers. Then the Tutte matrix becomes a matrix of numbers instead of symbolic, and its determinant can then be calculated using Gaussian elimination once it has become numbers rather than variables. Does that make sense? But this is, of course, evaluating such a multivariate polynomial does not help us directly in checking whether it's a 0 polynomial or not, because we might evaluate it accidentally at arguments which happen to be a root. On the other hand, we've just on the previous slide analyzed what is the probability for this to happen, to evaluate the polynomial at a root, although it's not a 0 polynomial. This is exactly the Schwartz-Zippel lemma. So baseline is using the Schwartz-Zippel lemma and using this theorem, the reduction from testing whether the graph has no perfect matching to testing whether the determinant of Tutte's matrix is identically 0. This gives rise to a very simple and efficient algorithm for testing whether the original graph has a perfect matching. And you will be asked later to implement this algorithm in LAs. It will involve 3 stages. First, implement the Schwartz-Zippel test, Blackbox test. That's simple, right? Just guess values for the variables and plug them in and evaluate them. Second step, implement the conversion from a given graph to the Tutte matrix. And third step, evaluate the polynomial representing the determinant of Tutte's matrix on given values. Or put differently, guess values for the variables according to Schwartz-Zippel. Then plug in these values into Tutte matrix, thus converting it to a number matrix without variables. and then use Gaussian elimination to evaluate the determinant of that matrix, putting it into echelon normal form. Okay, so that's the algorithm, and the analysis follows from Schwartz-Zippel, and you are asked to amplify the probability to our standard bar 2 to the minus 100. So what remains now is for us here, not as part of your homework, to prove this important theorem in red, okay, right? So we need to prove that the determinant of Tutte matrix is identically 0 if and only if the original graph has no perfect matching, because this is what the algorithm is based on. But you can readily implement that algorithm, although we may not have proven this. No, we will prove this in a minute. There's a question by Robert, yes? Yes, thank you. Robert is asking, how do we convert the symbolic Tutte matrix into a numbered matrix? So there are two answers to that question. The first answer is, first we take the determinant of Tutte matrix, which does involve variables, and therefore the determinant is a multivariate polynomial. And we could evaluate that polynomial, we could compute that polynomial, we can represent that polynomial using Leibniz formula. But this gives rise to an inefficient algorithm. And then we could apply the Schwartz-Zippel lemma and plug in values for the variables in this polynomial. So first idea, take the graph. From the graph, form the Tutte matrix, symbolic Tutte matrix, form the determinant of the symbolic Tutte matrix, which is a multivariate polynomial. Express the polynomial in this way, and then plug in values for these variables randomly according to the Schwartz-Zippel test. Or, and that's a more efficient way of achieving the same, take the graph, convert it into the Tutte matrix as previously, which now involves variables, and now already guess values randomly for these variables according to Schwartz-Zippel, plug in values for these variables, thus converting the Tutte matrix into a matrix of numbers without values, but some of these values, only some of them are now random numbers, have been graded randomly. Other numbers are fixed to be zeros. And also there's this correlation between some of the entries, right? So if we assign a random variable to this matrix, to this variable x, then the entry in the Tutte matrix will be plus this random number, and this other entry, the reflected one, right? So this is basically transposing the matrix, right? So the entry in the transposed entry must then be the negative of the same value. So there's a correlation between the random numbers. So thus we arrive at the matrix whose entries are numbers, and then we calculate the determinant of that number matrix using our regular Gauss algorithm. So let me say it again. First approach, take the graph, convert it to a Tutte matrix with variables, form the determinant, which is a multivariate polynomial with variables, plug in random values for these variables according to Schwartz-Zippel, or mathematically the same but algorithmically more efficient, take the Tutte matrix with variables, plug in values already now random variables according to Schwartz-Zippel, thus arriving at a number matrix, and calculate the determinant of that number matrix, now without Leibniz and instead using Gauss algorithm. Robert, I hope that answers your question. Thanks for asking this question, and thanks for the opportunity to clarify this indeed subtle but very important point. Mathematically, it makes no difference at which stage we assign random values to the variables, but algorithmically it makes a huge difference. Okay, so, and this is the last slide of this chapter on randomized algorithm, where we indeed prove this theorem that the conversion from the perfect matching problem to the Tutte Matrix determinant problem. And the proof proceeds by proving 3 separate lemmas that then put together give rise to the theorem. And the first lemma says that one direction kind of, if the original graph, undirected, loop-free graph, has a permanent perfect matching, then the determinant of Tutte's matrix is not identically 0, it's not the 0 multivariate polynomial. That's the first lemma. So let's go ahead and prove that lemma. And so to this end we start, we look at a perfect matching in the sense indicated below. That is a permutation of the vertices satisfying these properties, that all cycles of this permutation have length 2, and every pair of a vertex and its associated spouse is indeed an edge of the graph. And now we look at that corresponding term in the Leibniz formula for the determinant. And in the Leibniz formula, we look at this term in the sum that corresponds to this permutation, right? So the sum is over all permutations, and therefore in particular it includes the permutation that we're currently interested in that realizes the perfect matching, the permutation that assigns to every vertex its unique spouse. And in this term for this permutation involves, remember the definition of the Tutte determinant, Tutte matrix involves a variable, right, plus xij, and since the spouse is also occurred here, so let's say this is a I here, the ith term, so this is from I to pi of I, and then so also of course the spouse of vertex I, which is called pi of I, also gets assigned back to the original spouse, which corresponds to another factor here in this huge product, right? So when I is here, then j is pi of I, and here when j is pi of I, then there's a corresponding term, but now with opposite sign, because precisely one of them is increasing order of vertices and one of them is in decreasing order of vertices. When proceeding from one vertex to its spouse and back, then one of the two vertices in the couple have larger index and the other has smaller. So one occurs with plus sign and the other occurs with minus sign, but they both refer to the same variable, xij, that is the same edge. That means this product, which is basically minus a squared variable, occurs here. And since we're talking about a perfect matching, that means every person here in this huge product occurs precisely once as such a quadratic expression of the same variable, so that the whole product here becomes non-negative. Nowhere occurs a zero. A zero occurring would namely mean that the permutation follows something that is not an edge. And since we're talking about a perfect matching, this will never happen. So that means the permutation here gives rise to a non-zero term here in this multivariate polynomial, and a non-zero term in this polynomial means that the entire polynomial also is non-zero. And this is exactly the claim of lemma 1. So to summarize, if the graph G has a perfect matching, then indeed Tutte's the determinant of Tutte's matrix is not identically 0. That's one direction of the theorem, right? So, right. So if G has a perfect matching, then the determinant is not identically 0. That's a contraposition of one direction. So it remains for us now to prove the converse. Namely, if the graph has no perfect matching, then the determinant is identically 0. And this is what the remaining two lemmas are about. And to this end, let's introduce an abbreviation in the Leibniz formula. For every permutation that occurs here, this is a monomial, right? Possibly 0 whenever there occurs 0 somewhere in this product, and the entire product will be 0. And this monomial will be abbreviated with m pi. M for monomial and pi for the permutation we're currently looking at. And some of these monomials will be 0, namely whenever there occurs a 0 somewhere in between. And otherwise, it will be just a product of variables, like the one we just saw and exhibited in the proof of the lemma 1. And lemma 2 says, if we have a permutation that whose cycle decomposition is only involves even cycles only, then that monomial will be not identically 0. So let me say that again. No, that's a hypothesis, sorry. If we have a permutation that is composed only from even cycles, remember every permutation has a cycle decomposition, and if all the cycles in this decomposition are even, and if for such a permutation the corresponding monomial here is not identically 0, then the graph has a perfect matching. So that's a partial converse to lemma 1. Lemma 1 says one direction in this equivalence, if and only if. And lemma 2 is a partial converse, namely only for permutations in this sum that are composed of even cycles only. And lemma 3 will take care of permutations involving also at least one odd cycle. And then together, lemma 2 and 3 will provide the converse of the theorem. Okay, let's move on to prove the lemma 2. So we're having a permutation pi that consists of even cycles only. And let's look at the, we want to show that the graph has a perfect matching. So here's some graphs that have cycles of different lengths. So here you see a graph that has a cycle of length 3. So if we have a permutation that involves a cycle of length 3, then we cannot conclude that this graph has a perfect matching, right? If we have a graph that involves a cycle of length 5, then again, we cannot conclude that this graph has a perfect matching because odd number, right? But here, this is the case we're interested in. This is what lemma 2 is talking about, namely permutations that only involve edges, right? So let's say this vertex gets mapped to this one, this vertex gets mapped here, this gets mapped here, and this gets mapped back here. So this is a picture, one way of a permutation of length 4, or the other way around. That's also fine, right? But this is not a perfect matching, right? It's not. On the other hand, this graph has a perfect matching. The permutation is not a perfect matching. Perfect matching requires all cycles to have length 2, but it has length 4. On the other hand, it has a perfect matching. Namely, just decompose the graph in this way, cut the original permutation into two parts, into two cycles of length 2. And this is true for every permutation consisting of even cycles only. If the cycle already has length 2, then we're good. If the length is 4, then we decompose it into two cycles of length 2, and so on. So a permutation composed from equal cycles only immediately gives rise indeed to a perfect matching. And this is a proof of lemma 2. Okay. what remains to treat is the case where we have here in this Leibniz expression for the determinant of Tutte Matrix some permutation such that the monomial here is non-zero, but the permutation involves some odd cycle, at least one odd cycle. And this is what lemma 3 is about. Suppose we have a permutation pi and consider permutation pi prime, which agrees with pi, except that one odd cycle of pi is reversed. So more precisely, let's say it again. Suppose pi is a permutation that involves, among possible even cycles, at least one odd cycle. Take that odd cycle and reverse it, and let pi prime denote the resulting permutation, where this one of the odd cycles is reversed. Then the claim says if we consider the following according monomials, the monomial assigned to pi and the monomial assigned to pi prime, then these two monomials have opposite sides, assigns. That's the claim. Now let's see why this is the case. Let's look at the monomials. First observation, the sign of the two permutations remains the same. So we have these two permutations, pi and pi prime, and both agree except for one odd cycle in pi is being reversed in pi prime. How does that change the parity of the number of odd cycles? It doesn't, right? Because the number of odd cycles remains the same for pi and for pi prime. Only orientation from one odd cycle gets reversed, but the number of odd cycles is the same in pi and in pi prime. And in particular, the parity, the question whether the number of odd cycles is even or odd, also remains the same. So therefore, the sign is the same. And now let's look at the rest of the monomial. So what happens if we reverse one odd cycle? If we reverse one odd cycle, that means that all these signs get flipped, right? So when previously a vertex with smaller number gets mapped to a vertex with larger number, then after reversing, the vertex with large number gets mapped to the vertex with smaller number. And therefore the sign flips, or vice versa. If previously a vertex with large number got mapped to a vertex with smaller number, then after reversing the cycle, the vertex with larger number gets mapped to the vertex with smaller number. And that applies to every single part of this odd cycle. And since the odd cycle consists of an odd number of these sign flips, that means that the total number of sign flips is odd, and therefore the overall sign gets flipped in this monomial. And this concludes the proof of lemma 3. And now let's put lemma 2 and lemma 3 together in order to finally prove the converse direction of this main theorem, namely the direction where we suppose that the determinant of the Tutte matrix is non-zero. So this huge sum is non-zero, and we want to prove that then the graph has a perfect matching. And to this end, we decompose the sum here into those permutations which consist of even cycles only, and those permutations which involve at least one odd cycle. That part of the sum that involves only permutations involving at least one odd cycle, according to lemma 3, that part of the sum is identically zero, because to every term in this sum that involves a permutation with at least one odd cycle, it also, the sum contains also the permutation pi prime. And this permutation is also a permutation involving one odd cycle, but with negative sign, so that these two cancel. And more generally, that part of the sum that involves only permutation with at least one odd cycle, all cancel away pairwise according to this expression. So there's one expression with m prime and one with m prime with pi m, and both occur here, so they cancel each other. So this is not we can ignore that part entirely. So the interesting part in this sum is those permutations that are composed from even cycles only. And since the rest of the sum is identically zero, and our hypothesis is that the entire sum is not identically zero, therefore, according to lemma 2, there must exist a perfect matching. So let me say that again. One direction of the theorem is covered by lemma 1. If the graph has a perfect matching, then the determinant of the Tutte matrix is not identically zero. And the reverse direction is from lemma 2 and 3 together. Namely, if this determinant, if this huge expression is not identically zero, then we decompose this expression into that part of the sum involving only matrices with at least one odd cycle, and that part of the sum involving only permutations with even cycles only. The first part involving cycles with at least one odd cycle is identically zero because there these two contributions cancel away each other pairwise. So what remains is the part of the sum involving only permutations with even cycles only. And since the whole expression is supposed to be not identically zero, this part must not be identically zero. It must involve a monomial, which is not identically zero. And there, lemma 2 guarantees that there exists a perfect matching. So that concludes our proof of this main theorem about the determinant of Tutte matrices, and that justifies it's a purely mathematical statement, right? But this mathematical insight is the basis to an efficient randomized algorithm for testing whether the graph has a perfect matching. Namely, take the graph from the Tutte matrix and test whether the determinant of the Tutte matrix is identically zero using the Schwartz-Zippel test, which proceeds by plugging in random values for the variables in either the determinant or already in the original Tutte matrix. Okay, so to conclude our chapter 5 on randomized algorithm, we've talked about motivation. We've seen that the unreliability of randomized algorithm can be made so small that it becomes comparable to the probability for even a superficially deterministic algorithm to make an error because of some hardware or other source of failure that the algorithm cannot keep control. We've talked about sources of randomness, real random bit sequences, real random numbers as opposed to pseudo random number generators. We've distinguished between Las Vegas and Monte Carlo types of algorithms, kind of the trade-off between having a running time bound guaranteed or expected and having a guaranteed output versus having a random error probability. We've looked at the problem of primality testing, a nice example with a Miller-Rabin test, typical problem with one-sided error. We've seen that we can amplify the reliability for one-sided errors by repeating the algorithm with and the random coin flips. We can also amplify the reliability of algorithms with two-sided errors by taking the majority of the outcomes of the answers. This involves this famous Höftings inequality, purely mathematical claim. Then we've looked at the Blackbox multivariate polynomial identity testing, the Schwartz-Zippel lemma bounding the probability of this one-sided error for this generic randomized test. Just guess some values of the polynomial and plug them in to see whether this yields 0 or not. It was a very nice and elegant proof by induction on the number of variables involved. Then we talked about perfect matching in graphs, which superficially is a very hard problem because it seems to involve all possible subsets of edges, of which there are exponentially many. There exists a deterministic algorithm by Jack Edmonds, but it's a rather complicated algorithm, both in implementing and its analysis involving advanced graph theory. Instead, we've looked at a very simple randomized test, namely by converting the question whether the graph has a perfect matching into the question whether the determinant of its Tutte matrix is identically 0 as a multivariate polynomial. And we've proven that this conversion, this reduction is indeed correct, preserves or converts graphs with which do have a perfect matching into determinants that are identically 0 and vice versa.